introduced the PhD, but I am a PhD student until now at Ewha Women's University. Today, I will talk about efficient verifiably encrypted signature without random workers. First, I will tell you briefly the basic background and how we need this. And in PKI, there are some overhead problems. So to overcome this problem, in 1984, IDPKC was introduced by Kamil. However, there have been many studies for VS and verifiably encrypted signature in PKI. So we need more and more efficient verifiable and more efficient signatures. This motivated our signature. So I will introduce the verifiably encrypted signature. We simply call VS. VS is composed entities A, P, and T. A is a signer, B is a verifier, and the T is an adjudicator. The definition of the VS is a signature scheme satisfies the following properties. Signer generates the sign and signature, verifier confirms the VS, and the T only can recover the signature by using the private key. Simply examine the algorithm. A signed a message, and then B verify the VS by using the APK. This the point. B verify the VS by using the APK, and then if something wrong happens, the TTP will be able to extract it by using his private key. In this slide is many reference related works, and in this work we propose an efficient VS in standard model, and we prove the formal security of our scheme. I will examine the definition of the VS. A VS scheme consists of the 7 algorithms. A VS scheme that first through the third steps are the ordinary steps, and next the remainders are the newly defined. So A performs the fifth step, and B performs the 6th step, and T performs the 4th and 7th steps, and 5th step is equal to encryption of the 2nd step using by APK. APK is the public key of the T. In VS schemes, safety is first to verify the validity. The meaning of the validity is 2 things. First one is the validity of the VS, and the second one is the validity of the adjudicated VS. And the unforgeability and the opacity should be proven for the VS. Unforgeability is difficult to forge a valid VS, and opacity is difficult to extract an ordinary signature. Next to one is I will give VS scheme we invested. Our VS scheme is based on Q-strong Diffie-Hellman problem. We briefly call them QSDH problem. In key generation algorithm, given system parameters and output the private and secret key for the signer. And in these are the ordinary signature. These are same the given ordinary signature. So as you know, in sign algorithm, given this one and output this signature. In verify algorithm, given this one, that check the validity of the signature. This is the newly defined algorithm in ADJ key generation algorithm. This is the algorithm for the generating the key pairing for T. So in given system parameter and output the key pair for the T, and in V-sign algorithm, given this one and the VS signature. In verify algorithm is the check the VS. So the method of the check, the following equation holds. If it holds or the accept, or if others or the reject. So last step in adjudication, given this ones and output the ordinary signature. This one is the before step in this one. So this VS scheme is the given the ordinary signature, we encrypt the signature, and that is the same as the VS. This slide is the security proof. In this step, we first check the validity, but we already check the validity for the VS in VE verify step. So we need to check the validity of the adjudicated VS. So we check the one equation, and then we just prove the if VS if there is a forger for in VS, then we can make a forger a gentle signature. So in this picture, in this step, query and response between two forgeries can be communicated. In this picture, in Gentry signature, the PK and the APK are sent to VS forger, and by VS signed query and ADJ query can be obtained the response. So, and then this step is output the ordinary signature. So this is the complete of theorem 1, and second property is the opacity. Is the if is the same as the in theorem 1 VS scheme. If QSDH problem is hard, then the VS scheme is opaque. So this method of the proof in is the same as the in theorem 1. So in this picture, like this, in QSDH problem, the pH and APK are sent to via opacity attacker or forger, and via sign query and ADJ query. And by these queries can be obtained response, and then this provider can solve the problem. So using this algorithm, we will complete the proof. So first, check the validity and prove two theorems, and then our VS scheme satisfy the full property. So I omit the detailed proof. Efficient. Compare our VS scheme with some other VS scheme. The results are shown in table 1. PK is the size of the public key. C is the signature length of the signature. Gen and verify are the shows the computational cost like this. P is the pairing, E is the exponentiation in group, K as the output length of the hash function. And one fact, long denotes if the security proof use a random walker. If not, we note SM, standard model. In this table, compared to other schemes, our scheme is more efficient than others. So our VS scheme is efficient VS. In conclusion, we propose an efficient VS based on Gen2 signature, and we analyze the security of our scheme. So keep